So this evening we have the exam, right? Okay, now last time we defined surface patch and well, surface patches, and we gave several examples. Today we will do computations. So this is, I guess, 4.2 section 4.2 patch computations. Okay, let x from D to R3 be a coordinate patch for some surface, and U0, V0 is a fixed point in the domain. Then the functions taking U to x of U V0 and V to x of U0 V define two curves passing through the point x of U0 V0. So let me draw you a picture. Here is our, let's say, D, and this is our point U0 V0. Okay, and here is our surface in R3. Okay, this U0 V0 is this point, so this is our surface patch. Okay, and then what we do, we consider the two lines, this one and this one. Okay, the images of these two are curves like this, right? On this surface, right? Images of these two. Here you keep V0 fixed and you change U, okay, the first coordinate. So it is the V0 is fixed, it is the red one. And then here you keep the first coordinate and you change V, so it is the second one, the green one. And their images are two curves like this. Okay. Of course, these are just space curves, right? Because we are in R3, the image is in R3. So I can talk about all the, apparatus about curves like tangent vectors, normal vectors, binormal vectors, curvature, and so on, right? And here we will define the tangent vectors to these curves, and we will give them some special notation. The velocity vectors of the above parametric curves parameterized like this, okay, are denoted by okay, so what is the notation? So it will be just du of xu v0 evaluated at, so I take the derivative. So this is the derivative of this curve at the point u0. Here u is the variable, right? I keep the second coordinate fixed. This will be denoted as follows: x sub u u0 v0, and the second for the second curve, this time I keep the first coordinate fixed and let the second one vary, and I take derivative with respect to the second coordinate at the point v equals v0, and that will be denoted by x sub v u0 v0. Okay, so that's the notation. And here let me just describe them here. So this is just, let's say, x sub u u0 v0, and let's say this is x sub v u0 v0. Okay, two tangent vectors. My picture suggests that, you know, these two tangent vectors are perpendicular to each other, but it doesn't have to be. Okay, it is just, you know, my picture. All right, of course this is the point. This point is just what? This is just x of u0 v0, right? This point. Okay. Now, if x of uv has coordinates, right? This is a point in 3 space, so it has 3 coordinate functions: x1 uv, x2 uv, and x3 uv, right? Then the vectors, these velocity vectors, can be written as what? What is x sub u u0 v0? This is the derivative of this vector valued function with respect to u at the point u0 v0. So this is nothing but, let me write it this way: del x1 del u, and then del x2 del u, and del x3 del u at the point u0 v0. Okay, and the second one, the second velocity vector, is just the vector formed by the partial derivatives with respect to v. Again, this is computed at the point x0, sorry, u0 v0. All right. Now let's give some examples. Okay. Right. Since we are doing differential geometry, as in the case of curves, we will just take derivatives, right? And these are the first derivatives. later we will take the second derivatives and give meanings to those derivatives. So let sigma be the sphere, centered at the origin, with radius r. Then the spherical coordinates define a coordinate patch given like this, just r times cosine u, cosine v, cosine u, r times cosine v sine u, and r times sine v. Okay, where u is in the interval minus pi, and v is in the interval minus pi over 2, So in the UV plane, we have this region here. So this is pi, and then minus pi over 2, minus pi over 2. So this is my region D, right? It's open, of course. And then here is the surface patch X. Okay, so let's say X1, X2, X3. And if you have a point, okay, now I have the sphere. Suppose you have a point here. What are the coordinates of this point? Spherical coordinates. You look at these two angles. So cosine u cosine v. U is this angle. U is this angle. And then sine v. Sine v olduğuna göre sure, it's this angle. The z coordinate is sine v times r. Okay, so these are the two angles. Now this is a coordinate patch for the sphere. Now let's compute x sub u and x sub v. What we will do, we will just take derivatives with respect to u and v. So let's do that. Then the velocity vectors. So what is x sub u? Well, it is just the derivative of this gadget with respect to u. So it will be what? Minus r times cosine v sine u, and then r times cosine v cosine u, and then derivative of this with respect to u is just 0 because there is no u in it. And what is x sub v? This time we take derivative with respect to v, so we get minus r times sine v cosine u minus r times sine v sine u, and then r times cosine v. Okay, so our velocity vectors are these vectors. Sorusu olan var mı? Any questions so far? Okay. Okay, I have a definition. A regular mapping X from D into R3 whose image lies in a surface M is called a parametrization. Parametrization of the surface of the region. Sorry. Of M. Of course, this is very similar to what we call the coordinate patch. So a coordinate patch is a one-to-one proper parametrization. So we define something called parametrization. It is a little bit weaker than a coordinate patch. Okay, what we ask is that it will be a regular mapping. In other words, its derivative is never zero. Okay, its derivative is never zero, and the image lies in the surface. But it doesn't have to be a coordinate patch, meaning that it doesn't have to be one-to-one, and it doesn't have to be a homeomorphism onto its image. Okay, so we don't require those. Such a mapping will be called a parametrization. Now, this is a coordinate patch. This is a coordinate patch for the sphere, but the one I will just write down will not be a coordinate patch. It will be just a parametrization. Parametrization is something weaker, but it is sometimes handier. You know, it's easy to work with. Okay. So let me okay. Example, the map X defined from R2 into R3 by given by this UV. Okay, I will write the same expression. So R times cosine V cosine U, R times cosine V sine U, and r times sine v. This thing is a parameterization, okay? But okay, is a parameterization of the sphere. The advantage of this is that it is onto, it covers the whole sphere. You know, coordinate patch, coordinate patch, a coordinate patch usually doesn't cover the whole surface, right? This covers almost all the surface, but some circles are left out, right? The ones corresponding to u equals pi and v equals pi over 2, okay? Those are missing. However, here, this is onto, it covers the whole thing, but of course, this is not a surface patch because it is not one-to-one, right? It is clear that it is not one-to-one because I have sine and cosine, and here my domain is the whole R2. But the advantage of this is the following. You may just restrict your domain into smaller sets and you get surface patch for your surface at every point, okay? Namely, you know, this is R2 UV, and this is my sphere. Suppose you are at this point, just pick any point here, okay? Pick any point which is mapped to this point. Okay, okay, let's say this is the point P and it's mapped here. What can I do if I just choose a small set, open set here? That will give me a coordinate patch near this point. For some other point, I will use the same expression, but this time I may have to choose another region. So this is, let's say, in domain 1 and then domain 2. Restrictions of your parameterization to this, you know, small sets will give you surface patches at any point you want. The nice thing about this is that this formula doesn't change, okay? It is the same formula. But you have to distinguish a parameterization from a surface patch, okay? They are not the same thing. This is not a this is not necessarily a one-to-one map, therefore it doesn't have to be a proper map, right? It doesn't have to be a homeomorphism. Yeah. Well, usually we work with surface patches because you want an exact copy of your surface on R2. Okay, so it has to be one-to-one and onto. Maybe a small portion of it, but you have to have, you need to have the exact copy of that. If you have a parameterization, you are not sure about it. You know, some points on your domain may be mapped to you know, same point. So your domain and its image on the surface might be actually topologically different things. So it is better to work with surface patches. And this is what we are going to do all the time. But to obtain a surface patches, it is convenient to find a core parameterization, if there is any, which is defined, whose image covers the whole surface, and then you just use the same parameterization as a surface patch at any point you want. Okay. Well, if it is not, if the map is not regular, so if the derivative is not injective, then the image may not be a surface. Okay, so image could be something like this, for example. You know, a gadget like this, and you know, something like this is not a surface. You know, you don't want sharp edges or corners on a surface. You don't want those. And to avoid those things, you need to have your surface patch to be a regular map, so that the derivative is always injective, which means that at any point you have tangent vectors. Okay, here you have tangent vector in this direction, but you don't have a tangent vector in this direction, because you know, on the other part it goes like this. So that's a problem. Okay. All right. Here, you know, note that X here is not 1-to-1, so that it is not a surface patch. Okay. This thing is not a surface patch, but its restrictions to these small sets, okay, properly chosen small sets, are surface patches. The nice thing, as I said, you have the same formula which works at all points. Okay. All right. Okay, now we have the following. Let's consider the cross product x sub u cross x sub v. Right, I have two vectors on the surface, right, on the surface. Let's say x sub u and x sub v on your surface, right? Tangents of these curves passing through this point. I may consider the cross product. And what is that? Bunu sadece küre için yapmış aslında. Okay, let's do that. For the sphere, this computation is done. So what's that? U1, U2, U3, and here, if you, okay, so x sub u and x sub v are here. Right, I just take those and write as the rows of that matrix. And if you do that, So this is just cosine V sine U, cosine V cosine U and 0. Here I have minus sine V cosine U minus sine V sine U, and then here cosine V. And here actually I have R term here, another R here. So I have R squared. And the result is this vector, cosine squared V, cosine V, cosine squared V, sine U, and then cosine V, sine V. And if you take norm of this vector, norm squared, no, norm of this, what is the norm of this vector? It is just R squared. You square all these and add them up. When you square this two, you get cosine squared, sine squared, so it will be 1. And here's the common term will be cosine to the power 4. Yes. Yeah. Okay. Oh, okay. This is not correct. So sine plus sine and cosine V, and then sine U squared. Cosine V, sine V, and cosine squared, no, sine squared U. Okay. So when you değil mi? Sine and cosine, yok bir dakika. Sine, cosine, and then sine squared plus sine, cosine, cosine squared. No, I don't have this. Evet. Şimdi bunu çarpıyorum. Sinüs kare, kosinüs, sinüs. Burada kosinüs kare, sinüs, kosinüs. Dolayısıyla sadece sinüs, kosinüs var. Tamam. Bunun normunu aldığım zaman bunun karesi, bunun karesi, bunun karesini topluyorum. Bunun karesiyle bunun karesi kosinüs üzeri 4 ediyor. Bu şuna eşit değil mi? Cosine square, no, fourth power plus cosine squared V, sine squared V, and here I take cosine square parentheses. I have sine squared, cosine squared, which is 1. So I have just R squared cosine squared V. Okay. And you see that this is not 0 if V, okay, so let me write it, is not 0 if V is not if V is in pi over 2, pi over 2. So that these two vectors, x sub u and x sub v, are linearly independent on this region, right? On this region, meaning that the derivative map of x is injective, right? This means the derivative map of x is injective. So x star. If v is in pi over 2 pi over 2 minus pi over 2 pi over 2. So on this region, okay, on this region, the derivative of x is 1 to 1, so that this coordinate, no, this parameterization is a regular map. Okay. Şey için söylüyorum bunu. Okay. The reason we did this computation is because of the following. For a parameterization, x has to be a regular map, meaning that the derivative has to be injective, right? Let me show to other friends. Right. Here in the definition, we have regularity, meaning that the derivative of x has to be 1 to 1. And that's the computation, okay? That's the computation here. We show that these two vectors are linearly independent. Therefore, this is injective, meaning that x is a regular map. So it's a parameterization. Okay. To be a parameterization, basically you have to have just that the derivative map is 1 to 1, okay? All right, let's see another example of parameterization. Surface of revolution. Last time we studied these surfaces. So let alpha u, gu, hu, and 0 be a curve in the xy plane, right? The z coordinate is 0, meaning that the curve lies on the xy plane. Then as we have saw earlier, that a parameterization is given by x sub uv. What we do, we just take this, right? We just take this. Okay, let's say x, y, and z. So this is our curve, okay, alpha. We just take this and rotate about the x-axis. Değil mi? Öyle yapıyoruz. So you just rotate this about the x-axis. you get something like this. Okay. And remember that this is given as follows. So the x coordinate doesn't change because you are rotating about the x-axis. Meanwhile, y coordinate is just hu times cosine v and hu times sine v. Here, u is in I. Let's say alpha is defined from an interval into R3. It is that interval. And what about v? V can be any real number. So x is defined on an interval cross real line, okay? And its image is in the surface M, which lies in R3. Right, again, this function is not one-to-one, right? Because if you increase v 2 pi units, cosine and sine will take the same value. So this is not one-to-one. X is clearly not one-to-one. So it's not a surface patch, but it's a parametrization. So to show that it's a parametrization, we have to just show that the derivative map of x is injective, right? A parametrization is a regular map, meaning that the derivative should be injective. Let's check that. You see the derivative map, x says in general x uv is just x1 uv, x2 uv, and x3 uv. And what is the derivative map of this at any point? It is given by just the matrix, right? So x sub, I just take derivatives of this, x1 with derivative of x1 with respect to u, derivative of x1 with respect to v, and then derivative of x2 with respect to u, derivative of x2 with respect to v, and so on. Right, this is the derivative map. And to show that this is one-to-one, you have to show that this has rank 2. Rank of a matrix is equal to the column rank or row rank. In this case, we just show that the column rank is 2, meaning that these two columns are linearly independent. How can you check whether two vectors in R3 are linearly independent or not? You just take cross product. If it is not 0, it means they are linearly independent. So x star is one-to-one or equally injective if and only if its columns are linearly independent. This is equivalent, hence x star is injective if and only if x sub u cross x sub v is not 0. Okay. So let's do that for this surface patch. not surface patch, parameterization. So in our case, let me write XUV one more time. This is just GU and then HU cosine V and then HV HU sine V. So what is X sub U then? Derivative of this with respect to U. So it is just G prime U, and then derivative of this with respect to U, it is just H prime U cosine V, and then H prime U sine V. What about X sub V? Derivative with respect to V. This will give me 0. This will give me just minus HU sine V, and then HU cosine V. Now, what is the cross product? X sub U cross X sub V. Well, that is just U1, U2, U3. So here I have G prime H prime cosine V, H prime sine V, and then I have 0 minus H times sine V, H times cosine V. And what is this? Okay, so this is H times H prime cosine squared V plus H times H prime sine squared V. So this is just H times H prime. And then I have this. Okay, so just G prime times H minus G prime times H cosine V. And then the last one is minus G prime times H sine V. Okay, so this should be non-zero, right? This should be non-zero. Sorry? Yeah, well, the vector is non-zero if and if its norm is non-zero, right? Okay, so what is the norm? Square of this plus square of this plus square of this. So square of this 2 is just G prime squared plus H squared. This is just H squared plus H prime squared. So when you square all those, you get H squared times H prime squared plus G prime squared. And then you take, of course, square root. Okay. So therefore, for our surface to be, sorry, for this function to be a parameterization, this quantity shouldn't be 0. So this is not 0 if and only if H shouldn't be 0 and the gradient of alpha, right? So both of them shouldn't be 0. So this thing, no, this is just, so this shouldn't be 0. Meaning that your curve should have a non-zero velocity vector alfa, değil mi? Alfanın türevi 0 olmamalı. So you shouldn't have corners on alpha. Alpha shouldn't be something like this, okay? It should be a regular curve in the plane, And also it should be above the y-axis, right? So your curve should be like this. You know, this h should be non-zero. It should be above the y-axis. Sorry, x-axis. So for this thing to be a parameterization, your curve should be like this, meaning that at each point you should have a tangent vector, and it should be above the x-axis. It shouldn't touch the x-axis. Okay, then what you get is a surface actually, and this is a parameterization. Okay, now let's have a break. After the break, I'll continue.